Hello everyone and welcome to the TOMILO interview room. I'm your host, Yuan. Today, it's a special honor to invite our automotive parts expert, Senior Solution Director, Mr. Liu, to have an in-depth discussion with us about environmental testing for automotive components. Hello, Mr. Liu.
Hello, Yuan.
First, I'd like to ask Mr. Liu, why do we choose to focus on the topic of environmental testing for automotive components for this session's sharing?
Well, nowadays, the new energy vehicle industry is advancing rapidly. In 2024, global sales exceeded 15 million units, with the Chinese market accounting for over 60%. Behind this explosive growth lies the deep transformation of the automotive industry towards intelligence and electrification. Hot technologies like autonomous driving and smart cockpit interaction have given rise to a large number of new component types, such as LiDAR and high-definition cameras. The reliability of these components directly determines the stable operation of the vehicle and driving safety. At this point, reliability test chambers become the loyal guardians of quality. They can accurately simulate various extreme environments, identify potential issues with components in advance, and build a solid line of defense for vehicle safety and reliability. Ultimately, environmental testing is the crucial link connecting the development of net technology with its safe implementation.
Indeed, automotive safety is a top concern for every family. Let me ask another question everyone might be curious about. Which parts of the car does the environmental testing we're discussing today mainly cover?
Well, if categorized by the type and function of the parts under test, it mainly focuses on three major categories, which basically cover the core components of the vehicle. The first major category is interior components, like the central control screen, seats, car audio system, headliner, trunk, and other assemblies. These are key areas that directly interact with the occupants. The second category is exterior components, like LiDAR, onboard cameras, lights, sunroof, tires. These are constantly exposed to the outdoor environment. The third category is automotive electronics, such as various controllers, airbags, drive motors, engine control units, the vehicle's wiring harnesses, and various sensors. These are essentially the brains and nerves for the vehicle's intelligent operation, just as shown in this diagram here.
Listening to you, it turns out that so many components in our everyday cars must undergo stringent environmental testing before being installed. Next, let's focus on the test scenarios. To ensure the safety and reliability of these components, what specific multi-dimensional tests need to be performed?
Well, different components have vastly different usage environments, so we need to tailor the approach based on their test scenarios. They are mainly divided into three broad categories, and each category corresponds to actual, typical scenarios in real-world vehicle use. The first major category is temperature and humidity simulation scenarios. This is the most fundamental and core scenario, covering almost all components. For example, for automotive interiors, after a car is exposed to the sun in summer, the cabin temperature can reach 60 to 80 degrees Celsius, requiring simulation of high temperature and high humidity. We can simulate conditions like 40 degrees Celsius with 90% relative humidity to verify the stability of electronic devices inside the cabin. In winter, the cabin temperature can be very low. Here, we can simulate scenarios like minus 30 degrees Celsius or minus 40 degrees Celsius to test the resistance to brittleness and cracking of dashboard plastic parts. The second major category is the exterior components we just mentioned, which are constantly exposed outdoors. In northern winters, temperatures can reach minus 40 degrees Celsius. At this point, we need to test, for instance, the impact resistance and resistance to embrittlement of components like bumpers in such low temperature environments. In the south, it's characterized by high temperatures and rainy weather. We need to simulate such high temperature and high humidity conditions. For example, cycling between 30 degrees Celsius and 60 degrees Celsius, with relative humidity from 60% to 95%. This cyclic testing verifies the aging resistance of light housings, preventing yellowing and cracking after long-term use. The third category is the automotive electronic components we just mentioned. Electronics in the engine bay operate long-term in high-temperature environments. Therefore, we need to simulate sustained high temperatures, like 80 degrees Celsius or 85 degrees Celsius, to test their stable operation and prevent failures under high heat. The second major type of test scenario involves combined temperature and humidity with other complex environmental factors. It combines other interfering factors encountered during actual vehicle use. The first subtype, for example, is UV plus temperature humidity combined scenarios for exterior parts. For instance, if a vehicle is parked outdoors long-term, UV radiation accelerates the aging of exterior parts. This requires an environmental chamber with UV functionality to simulate solar radiation, plus high temperature and high humidity, to test aspects like the color fading of trim strips and the coating adhesion of body panels, ensuring the longevity of both appearance and performance. The second subtype is for electronic devices. The combined scenario of vibration plus a wide temperature range. When a vehicle drives on different road surfaces, it generates continuous vibration. We need to simultaneously simulate temperature, humidity, and vibration to test the detection accuracy of radar sensors and the display stability of onboard screens, preventing performance failures caused by the combined effects of vibration and temperature, humidity. The third major type of test scenario is rapid temperature change validation. This type of test primarily verifies the structural stability and functional stability of the product under extreme temperature differentials and simulates long-term service life. For example, simply put, under conditions like seasonal temperature variations or drastic day-night temperature swings, it accelerates the aging process of components to pre-evaluate their reliability over the full life cycle, avoiding performance degradation later on.
These test scenarios are indeed closely aligned with actual usage needs from the perspectives of the user, the enterprise, and the industry. Why is it necessary to conduct these tests?
Well, from these three perspectives, the necessity for conducting these tests is reflected in four core dimensions that are mutually supportive and interlinked. The first is the most fundamental, ensuring driving and riding safety. Safety is always the core starting point of testing. For example, through high, low temperature stability tests on electronic components, we can effectively avoid risks like the vehicle system suddenly crashing in low temperatures, or failures in the battery management module at high temperatures, leading to vehicle loss of control. This is equivalent to building a safety protection wall for occupants from the source. The second dimension, the most basic one, is meeting regulatory and standard requirements. Whether in the international market or our domestic market, there are clear, mandatory technical standards for the compliance of automotive components. These test standards are the compliance passport. Passing these test standards is the compliance passport. If a product fails these tests, it is not qualified for market entry, let alone serving users. The third dimension, quite directly and immediately, improves user experience and brand reputation. For instance, aging resistance tests for exterior parts can effectively prevent issues like cracking after 1 or 2 years of use, or yellowing of light housings, problems that affect appearance and usability. Such issues, while seemingly minor, can directly cause user dissatisfaction and complaints. Conducting these tests helps avoid them in advance, both enhancing user satisfaction and helping companies accumulate a good reputation. The last dimension is crucial. It reduces costs for the enterprise. Many companies easily overlook the value of early-stage testing, but in reality, environmental testing during the R&D phase can identify potential component problems very early on, such as electronic device crashes under high heat or exterior part breakage in low temperatures. The cost of solving problems at this stage is only about 1/20th to 1/20th of the cost of recalls after mass production due to failures. Test equipment like environmental chambers are precisely the core tool for companies to control quality upfront and reduce losses downstream. Indeed, these four dimensions are progressive. Compliance is the foundation for market entry. Safety is the baseline for user trust. A good experience solidifies brand value, and cost control provides the fundamental guarantee for companies to continuously invest in safety and quality. Ultimately, it forms a virtuous cycle.
So there's so much involved in environmental testing. Mr. Liu, with so many components going through such complex testing processes, what are the main challenges encountered?
Well, I've summarized 3 main challenges. The first is the long test cycles and high operating costs. How to reduce energy consumption is a challenge faced by both chamber manufacturers and client companies. The second challenge is the wide variety of automotive components, leading to numerous testing standards. We need to meet both national standards and international standards, and also adapt to standards developed by the automakers themselves. For example, standards from Volkswagen, like the W80,000 curve, PV curves. BMW has its own specific curves. Toyota also has TS standards, and so on. If a company wants full coverage, they either need to purchase multiple pieces of equipment, or find a single device that can accommodate all these curves, which often keeps procurement costs high. The third challenge is that test equipment simulates real-world conditions to accelerate testing, validating component reliability over their full life cycle. This imposes very high requirements on the performance of the environmental chambers. Simply put, the accuracy of our temperature and humidity control. Its stability must be excellent. Otherwise, our test data loses its reference value.
So, does TOMILO have any specific solutions to address these challenges?
Well, targeting these difficulties, we at TOMILO have developed a set of solutions covering all scenarios. They can adapt to standard requirements and also meet customized needs. As you can see in this diagram, for the first category, targeting temperature humidity testing and high, low temperature storage tests, we have single layer and double layer constant temperature humidity chambers, A, B chambers, 3-compartment chambers, and large-sized walk-in chambers. These can be flexibly selected based on the size of the components. The second category is for combined tests involving thermal shock and complex environmental scenarios. We have introduced thermal shock chambers, rapid temperature change chambers, and combined environmental chambers integrating temperature, humidity, and vibration. These provide one-stop solutions for complex scenario testing. The last category is our advantage in customization. Besides standard model products, we can also design based on special customer requirements, such as for large body components or personalized testing needs. For example, we can create customized designs tailored to the standards of specific automakers, or multiple OEM standards. This helps companies avoid repetitive procurement of multiple devices. Simultaneously, we have our own professional technical expertise to optimize technology and reduce long-term energy consumption for our customers. Simply put, whether it's basic testing or complex scenarios, TOMILO can provide a precisely matched solution with cost optimization.
Mr. Liu, based on your introduction, TOMILO has a rich product portfolio in the automotive component testing field and also offers customized solution design. Could you share a distinctive case study with us?
Of course. Actually, I can share two distinctive cases today. The first one is our LiDAR testing solution. Looking at this image, we can see the appearance of the LiDAR inside the test environment. Its viewport is quite distinctive. For the viewport, we selected optical glass with a light transmittance greater than or equal to 93%. Around the viewport, we also configured an annular air knife to ensure no condensation forms in low-temperature environments. Inside the chamber, the LiDAR transmitter is placed while the receiver is positioned outside. The signal needs to pass through this glass pane. Therefore, the selection of this glass and the design of its placement involves certain technical challenges. Furthermore, to ensure the actual testing effectiveness for the LiDAR, we also designed a rotation mechanism for the LiDAR inside the chamber to truly match its real-world usage scenario. The second case I'll introduce is this airbag deployment test solution. Please take a look at this animated simulation video. You can see, this is a systematic solution that combines temperature humidity testing with airbag deployment testing. Additionally, it integrates a full set of automated equipment. Also at TOMILO in the area of thermal management, we have enthalpy difference test facilities. For headlight testing we have solutions and these characteristic 3-compartment chambers. These are all solutions with significant technical difficulty and distinctive features.
Judging from these design drawings, these environmental chamber designs are indeed very distinctive and represent TOMILO's customized products. Which major clients in the industry do we currently work with?
Well, we have successful case studies with leading clients in the industry. The first category includes OEM clients like BMW, Mercedes-Benz, Volkswagen, BYD, Li Auto, XPeng, etc. The second category includes component suppliers like Bosch, Continental AG, Fuyao, Hesai. The third category includes thermal management clients like Sanhua, Meiho, Borg Warner, Denso, etc. These clients are basically industry leaders or mainstream players. We have successful cases with other clients as well, which we won't list one by one here.
Good. It seems that in the automotive components industry, TOMILO has indeed accumulated extensive project experience and possesses deep technical expertise. Thank you, Mr. Liu, for your detailed answers today. We hope today's explanation has given everyone a deeper understanding of the automotive components industry. We look forward to seeing you in our next interview session. Goodbye.